All right. Hi, everyone. Like Aisha said, I was at the University of Washington this summer, and I worked on a really exciting project there that focused on the effects of earthquakes on episodic tremor and slip events on the Southern Cascadia subduction zone. And being at Washington was actually the best place to study this because it happens there often. All right. So just a brief background on slow slip and tremor. I've included a schematic cross-section of the plate interface. So what we see here is the Juan de Fuca plate subducting underneath the continental North American plate. And generally, when subduction happens, stress accumulates on the fault, and in the lock zone, it eventually breaks, which is a normal earthquake. And I'm sure many people are familiar with this. But in addition to these normal earthquakes that happen, these normal fast earthquakes, we have these slow slip earthquakes, and this occurs at the zone of free slip, which is between the locked and the stable slip zone. And generally, when we see a slow slip event, what we usually see normally is the Juan de Fuca plate subducting down the normal plate, the North American plate, which is an eastern trend. But when the slow slip event happens, we see the GPS move west. So in addition to being able to see slow slip and GPS, we can see a seismic signal, which is these wonderful colorful dots here, and that seismic signal is called tremor. And tremor is basically the rumbling or trembling of the earth. Okay. All right, so several scientists have studied how they've characterized normal earthquakes, and they've also studied slow slip events separately, but not many people have worked to understand how earthquakes and ETS interact. So a previous study, Iraqi 2017, looked at how 2 megathrust earthquakes in Japan could interact with ETS, and they found that these large-scale earthquakes could affect the dynamic stress of a subducting plate. So with that in mind, I worked with my mentor at the University of Washington to ask some questions about that. And we wanted to look at how ETS, which is episodic tremor and slow slip, I don't know if I said that earlier, but it's a mouthful, but we wanted to know how ETS responded to nearby earthquakes in the Southern Cascadia subduction zone. And specifically, I looked at the Mendocino Triple Junction, which is the Gorda Plate region that you can see here. I'll point to it, the Gorda Plate region. And I wanted to understand how, well, if they were interacting and if we see any kind of effect, and if we do see an effect, how does that affect the recurrence of ETS, these ETS events? Okay. So in order to do that, we had to look at the GPS time series and the seismic signal, which is the tremor. So just to walk you through here, these little blue dots are the GPS positioning, and you can see the sawtooth pattern. So generally, when the plate is subducting, like I said, it's moving east, and that's the upward trend. But whenever there's a slow slip event that happens, there's a dip, and that means it's moving west. So this is a paper from Draggart and Rogers that correlated the tremor and the GPS time series, and they found that they line up. So during every ETS event, we can see that there's a peak in tremor as well. So another thing to note is that tremor is always happening, but it's just during these events there's a peak. Okay. So for my study, I looked at 3 stations in the Southern Cascadia subduction zone. I chose station YBHB and DDSN, which is in 2 different places in the tremor belt. I included a 3D cross-section just to give you an idea of where we're at. But one of them is in Northern California, and the other one is in Southern Oregon as well. I included P160 just to show the earthquake events that I was planning on looking at. And the 3 earthquake events that happened in the Gorda Plate, Mendocino, Triple Junction region was a magnitude 7.2 in 2005, a magnitude 6.5 in 2010, and a 6.8 in 2014. So I wanted to look at how ETS was changing before and after each earthquake event. Okay, and just to give you an example of how a GPS station can see a normal earthquake, I've included P160, which is actually a plate boundary observatory station, which many of y'all are probably familiar with at UNESCO. But you can see that after every earthquake, there is an offset in the GPS, and it just shifts up. And that's pretty much why I included P160. But there's no tremor in station P160 because it's outside of the tremor belt, and it's just not in that zone where free slip is happening, slow slip is happening. Okay, so what I ended up doing was basically copying the Draggard paper, but using the PNSN GPS time series and matching it up with tremor here. Well, not here, but in the southern Cascadia subduction zone. And I worked to catalog these ETS events. So using a MATLAB code from my advisor's grad student, we got to get the 30-day average of the GPS positioning because it was pretty noisy at first. And the tremor that you see here is from 30 to 60 kilometers away from the GPS station. So the red marks here are all of the ETS events that I cataloged. This is not actually all of the events that I cataloged because it went back to 2001 for DDSN and 1997 for YBHB. But in terms of space, I just cropped it out to 2010 to 2018. Okay, so our results showed that the recurrence rate did not actually change. So for each event for YBHB, the recurrence for ETS was 0.9 years. It went to 0.8 years, to 0.7, to 1. So there wasn't really that much of a change that happened. And everything here has a standard error of 2 years. And for DDSN, it was the same thing. There was not really a change that went on. And that was pretty surprising for me because in the Iraqi paper, we saw that there was some sort of interaction between ETS and normal earthquakes in Japan. So I expected to see something change here. Okay. So why was there no change in ETS recurrence? I thought it was surprising because in the Iraqi paper, they were able to see an effect from the seismic waves 60 kilometers away from the actual tremor. So they also had similar earthquake magnitudes. So they had a 6.0 earthquake and an 8.1, which is similar to the 7.2, 6.8, and 6.5 earthquake we saw in the Gorda Plate region. So I found that a little bit surprising, but it makes sense because we concluded that it's possible that the orientation of these 3 earthquakes wasn't optimal to cause enough stress change in the subducting plate for the ETS fault. So it could just be that the earthquakes were not oriented right and it didn't affect the ETS recurrence. So that was pretty much what I found. In the future, it would be helpful to look at more stations. Today I only talked about 2 stations, but as you can see, there are several stations that I could have looked at. I did about 20, but in terms of presenting, I was only able to really confine to 2 stations. And in addition to looking at more stations, it would be helpful to do a Colloquium stress calculation to better understand what's actually happening with the stress changes in the fault. Okay. And just a couple of acknowledgments. I'd like to thank Nisha, who's my communications mentor, NSF and RESESS sponsors, University of Washington Slow Slip Group, PENGA, UNESCO, and PNSN for all of the data that I used today, and RESESS, of course. All right. Thank you.
my question is, you had to constrain to just 2 sites. How did you choose those 2 sites, and how are they representative?
Okay. So the 2 stations that I chose were YBHB and DDSN. They were, like I said, I showed the map of the Tremor belt that has, all this Tremor, the little colorful dots. So I wanted these stations because they do have a long GPS and Tremor history. So for, like I said, YBHB, it's 1997 and DDSN was 2001. But I also wanted those 2 stations because they were in the Tremor belts as well. I guess I can show you. So ETS events are seen in, they should be seen in most of all the central, which is the red dots here, central stations. So if I do see it in one, I would like to see it in a faraway station to make sure that it was actually an event. So I chose those 2 because they were spread out and in the Tremor belt, and they had a long history, basically. Yeah. Okay.
So in the previous study on the Nankai Trough, those other earthquakes that they were examining, were those earthquakes on the plate interface as opposed to the ones you looked at, which are on the strike-slip component of the system?
Yeah, that's a great point you brought up. I didn't actually bring it up, but the earthquakes that I looked at were strike-slip, and for the Nankai Trough study, the Iraqi one, they were looking at megathrust earthquakes, so it's different. Yeah.
Yeah, there's a real dearth of large earthquakes recently in the Pacific Northwest. The only other one I can think of is the Nisqually earthquake, which was 2001. I would have thought the ones over by the Mendocino area were a bit far away. Have you thought about maybe checking like Alaska? There is ETS there. It's not quite as well documented or quite as, and also less frequent than, and nice in the Pacific Northwest, but
yeah. Well, for the purpose of just this summer and working with the University of Washington, we were focusing mostly on the southern Cascadia subduction zone, just because there wasn't really a lot of work done there, and it's a pretty messy area in terms of tectonics.
It is. There's a lot of tremor I know, and
yeah. And so it was pretty hard to actually pick out the tremor events because it was really noisy just all the time. But it would be helpful to look at Alaska. I just didn't have the time, honestly. Yeah.
Okay, fair enough.
Yeah.
Anything else? Okay. Thanks, Annie.